All right, we're going to get started. Hello, everybody. Welcome to today's webinar, Fixing the Big Problem of Microplastics, How Infrared Microspectroscopy is Enhancing Chemical Identification and Research. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be your moderator for today's event. Today's webinar presenter is Dr. David Shearing. David is a founder and principal at Zytec, a small company dedicated to the development and marketing of vibrational spectroscopy products. He has more than 30 years of experience in the business of instrumentation for chemical measurements. Over the course of his career, Dr. Shearing has led and contributed in the development of groundbreaking vibrational spectroscopy technologies in the fields of infrared microspectroscopy, portable and handheld FTIR and Raman instruments and methods, vibrational spectroscopy applications in security and defense, and Raman spectroscopy for threat detection and airport screening. He has authored more than 25 publications on various aspects of vibrational spectroscopy and holds a PhD in analytical chemistry from Miami University, where he's also an adjunct assistant professor of chemistry. This webinar is brought to you by Quantum Analytics. We are a value-added distributor of analytical instrumentation. We offer an array of flexible instrument financing programs combined with technical services, installation, training, and product support. Quantum Analytics is a proud channel partner for Zytec's instrumentation in North America. As a registered guest, you'll receive a link to this recorded webinar in your email when it becomes available. This webinar, including Q&A, will last about 45 minutes. Type your questions at any time into the text box in the question module that you see at the right side of the screen, and Dave will answer them at the end of the webinar. This ends our introduction, so without further delay, I present to you Dr. David Shearing.
Thank you very much, Lauren, and thank you to Quantum Analytics for asking us to contribute to this webinar series. I'd also like to thank my co-author, Tony DiDomenico, who did most of the work that I'll be presenting today, and I want to thank you for attending. So now I'll begin talking a little bit about the problem of microplastics and how infrared spectroscopy is aiding the cause in mitigating this crisis. So what are we going to be talking today? First of all, we'll give an overview of microplastics, what they are and how they're found. We'll also talk about some instrumental identification methods, analysis methods, an introduction to infrared microspectroscopy and the SurveyIR Microanalysis Accessory that we used in all of the data presented today. We'll also talk about some of the sample preparation and collection aspects for microplastics specimens, and then we'll follow up with a conclusion. So, a little introduction to microplastics. The modern world thrives on plastics, and almost all consumer products involve plastics in some way, shape, or form. Annual plastic production has increased 20-fold in the post-World War II era. Plastics in the oceans first gained attention through aquatic animals being entangled in the nets, and more recently, also included in this presentation that we're showing, is images of aquatic animals that have mistaken plastic for food, and all of the bad things can happen when they do that. So microplastics is a very hot topic, and today, everywhere you turn, whether it's an article, a news flash, or a social media post, there's lots of information coming up about microplastics in the environment and in the waters, either the oceans or tributaries especially. So, what are microplastics? Microplastics are defined as plastic particles in the environment that are less than 5 millimeters in dimension. These microplastics can come in various different forms, including microbeads, fibers, or pieces of plastic that have been degraded or part of much larger pieces of plastics that they've become separated from. How do the plastics get into the environment? Well, it can be trash that is unfortunately dumped into or close to tributaries or the ocean. It can come from storm runoff over land, and it also can come from sewage plant discharges. So a little bit more of the background on microplastics. The earliest report that we found of microplastics noted in the environment came from the 1970s through a study of plankton on the east coast of North America. It's been estimated in 2014 that more than 5 trillion plastic particles weighing more than a 250,000 tons are floating in the oceans. Some waterways are so polluted with plastics that significant resources are needed to aid in the removal process. If you actually look at this photograph that came from Indonesia, these are military folks helping to remove microplastic trash from a waterway. Something that's come up very recently in the news and has garnered a lot of attention is the fact that microplastics have been found in bottled water that, of course, humans then ingest. So as we mentioned in the beginning, small and large animals can mistake these plastics for food. And when they ingest the plastics, if they survive, these plastics can work all the way up the food chain into humans. In the case of animals, the plastic particles can go undigested and block or disrupt the digestive tracts of many animals. And you see a real tragic example of this in the photograph and the quote in the balloon, but this is an albatross. And evidently, these species of albatrosses are very attracted to the plastics that are in the ocean. And you can see in the digestive tract of this albatross, very significant a quantity of plastics that the bird has ingested. Through chemical analysis, plastics have also been detected in shellfish and fish purchased from seafood markets. The long-term effects of ingested microplastics in animals are largely unknown. Styrene-derived plastics have been linked to disruption in the functioning of the endocrine system, and many studies have noted that plastics can absorb chemicals and pre-concentrate them into the plastic materials, and these toxic chemicals can then enter into the food chain and all the way up to humans. And this has been noted in one study that is described in the quote in the balloon. So luckily, governments and environmental groups have been taking note of the microplastic problem, and there have been some efforts to clean up and mitigate the problem. Most notably, governments have begun to ban the manufacture and incorporation of microbead plastics in cosmetic products, which these microbead plastics can then enter the environment when they're washed off of the human using the products. Many engineers and researchers have also come up with unique solutions to clean up plastics in the environment, and we have a couple of examples shown in the photographs on the bottom. So research into the long-term effects of microplastics and pre-concentrated or concentrated chemicals in the plastics are ongoing and will hopefully shed light on the far-reaching effects to our ecosystem. So what can we do? Mitigating microplastics in the environment relies first on accurately identifying the source. So larger plastics, such as plastic shopping bags and fishing gear, are easily identified, and these things are starting to be addressed. So microplastics, the identification of the plastic needs to be determined in the first step of the investigation process. And it's a global issue, particularly as it relates to the oceans. Shown on this figure in the bottom right are the ocean currents around the world, and extremely large quantities of microplastics have accumulated around these currents. I heard that in particular in the South Pacific, the size of the plastic area exceeds the state of Texas. So it's a really tremendous problem in the global oceans. So now let's talk a little bit about methods to identify and analyze microplastics. Specifically today, we'll be discussing infrared spectroscopy and more specifically, infrared microspectroscopy. So infrared spectroscopy is a mainstay analytical method for the identification of unknown samples. With modern technology, the sample preparation required to analyze the sample using the infrared equipment is minimal, and in some cases non-existent. And we'll talk a little bit about that during the course of the presentation. Infrared spectroscopy is non-destructive, so we are able to identify materials and analyze them via other techniques if we're able to locate them after the analysis. Microspectroscopy offers the same benefits as infrared spectroscopy, but allows us to identify these samples on a much smaller size and mass scale. Based on our work, infrared microspectroscopy is well aligned for the size of most microplastics that we've encountered in the environmental samples that we've come in contact with. There are other instrumental technologies, of course, which are required to fully analyze microplastics and characterize the microplastic problem. Raman spectroscopy provides similar information to infrared spectroscopy. Because of the wavelengths of light employed, Raman spectroscopy can analyze samples that are smaller. However, one has to deal with the fluorescence interference, and in particular, microplastic samples are coming from the environment, and they can be in a complex matrix. So fluorescence due to contamination, other contamination at very low levels, can render Raman analysis a non-starter in some cases. Gas chromatography mass spectroscopy is a trace method. In its normal implementation, one could not identify the identity of the microplastic, but can analyze at a trace level any other chemicals that are adsorbed into the microplastic material. Special technology in GC mass spec using higher resolution mass analyzers can also be used for the analysis of tissues of organisms. And then finally, scanning electron microscopy can analyze extremely small particles, but the molecular information from the plastic is not determined in scanning electron microscopy. With energy dispersive X-ray, one can get an elemental signature from the plastic, but not a molecular one. So a little bit about Fourier transform infrared spectroscopy, generally speaking, for those of you who may not be that familiar with the methodology. So we're operating in the mid-infrared portion of the electromagnetic spectrum, which is defined from 2.5 micrometer in wavelength to 25 micrometers in wavelength. And that corresponds to 4,000 to 400 wave numbers in frequencies. So in this region of the electromagnetic spectrum, absorption due to vibration of molecules lead to increases in amplitude of the fundamental vibrations of the molecules. So the bands that we see are due to infrared light being absorbed and the energy of the molecule or the material increasing through vibration of the molecules. And in this example, we're showing a couple of the vibrational modes of water, H2O, where they appear in the infrared spectrum and the vibrations that they're due to. So around 3,400 wave numbers are the oxygen-hydrogen stretching mode, and around 1640 wave numbers is the oxygen-hydrogen symmetric bending mode. So molecules with more atoms will have much more complex spectra than water, but that complexity in the spectra leads to a very specific fingerprint of the molecule and will allow us to identify unknowns by matching against libraries of known materials that we store in the computer attached to the instrument. So if we look at infrared spectroscopy and compare it to infrared microspectroscopy, infrared spectroscopy allows us to analyze materials in the milligram mass range and in the millimeters size regime. And it's a bulk technique, if not coupled with a microscope that allows one to pass infrared radiation through it. So when we do that, we can extend the detection capability down to picograms, 10 to the minus 12 grams, and in the micrometer domain. So with a beam condensing microscope optics, we can analyze microsamples using infrared spectroscopy. So shown in this slide are some very common materials that exhibit themselves as microplastics in the environment. And you can see from the signatures on the right-hand side that these materials have very different molecular absorption spectra in the infrared region. And two molecules with different molecular structures will not exhibit the same infrared spectrum. The infrared spectrum is a fingerprint of a molecule. It's actually a physical constant of a material. And we can utilize this diversity in signature to identify these materials, even in relatively complex matrices, without the need for separation. It isn't as powerful, nearly as powerful as coupling chromatography, but it is not uncommon that we can identify multiple components in a single infrared spectrum. The instrument that we're going to be using today for the microspectroscopy is a product called SurveyIR that was developed at Zytec. And SurveyIR is a relatively unique microspectroscopy device. It interfaces to virtually all commercial FTIR spectrometers. It has a number of ease-of-use features that allow the instrument to be used even by folks who aren't familiar necessarily with microscopy as a first discipline. It is also different in that it is like an accessory in the sense that the user can actually mount the device in a sample compartment and take it in and out as they would an infrared optical accessory. It has a single USB connection which handles all of the power and the data link between the microscope system and the instrument attached computer. We have a clip-on diamond attenuated total reflection element that makes it particularly easy to analyze many samples using infrared spectroscopy because you simply touch the sample with a diamond crystal and measure the spectrum by contact. Also different in this system versus other FTIR microspectroscopy systems is that we have a very large depth of focus and field of view, which makes it easy to locate samples. And it has a lot of power associated with a relatively low-cost device. In that, we can analyze samples in transmission, reflection, and attenuated total reflection infrared modes. Because it mounts into the sample compartment and uses the instrument's own detector, liquid nitrogen is not required. It is a very compact device. It's less than 10 pounds. And when coupled with today's small FTIR spectrometers, makes it a very portable device which can be taken out of the laboratory to the location of the samples for analysis if that's important. So we're going to talk a little bit about some of the performance attributes of SurveyIR before we go into some examples of microplastic analysis. But one of the areas where, although SurveyIR is relatively low cost and affordable, it's very powerful. So this is a unique feature for this device in that we can illuminate samples with oblique illumination, which is also called dark field sometimes. But for scattering samples like this microplastic, which is on the surface of a filter paper, in this case, this was a filtered water sample, and we see this little microplastic, you see excellent color contrast and superb resolution in these images. And this is probably almost the universal illumination mode that we utilize for microplastics, and it's very good for scattering samples. We can couple this illumination method with a diamond ATR, which we can observe samples through. Diamond is transparent to visible wavelengths as well as infrared wavelengths. So we can actually view specimens through the diamond and then also observe contact with the diamond crystal like we see on the right-hand side. This allows us the confidence that we're making contact with the sample and we're analyzing the area in which we intend to analyze. A little bit about how microplastics are collected for analysis and prepared for analysis. In the case of plastics collected from the oceans or tributaries, there are numerous different kinds of nets and filters that one can use to collect the plastics. Shown on this slide in the upper right-hand image is a Newston net. So this can be pulled behind a boat, and plastics can be collected in this way. We can also use filtration methods. This is a filter of a particular pore size. You could use selective pore sizes to collect the size of plastic that you're interested in. We can also used for plastics that are in sediment. We can drill core samples. And then in the case of animals or fish, we remove the digestive organs, and then we actually have to do some preparation to remove the organic material from the animal. And that is typically done with these animal samples with a very caustic agents, including hydrogen peroxide solutions and hydroxide solutions. So we have some examples in our presentation here of mollusk and crustacean samples where we utilize this type of method to digest the organic material. We filter this liquefied material. In some cases, fluorescent dyes are added, Nile red in particular. This allows for visualization of the microplastic and counting of particles for a quantitative view of the extent of microplastic in the organs. That's not something we're going to talk about today. The remaining material on the filter is dyed and then inspected visually using an optical microscope and in some case fluorescence microscopy. And then finally, we choose particles for microspectroscopic infrared spectroscopic analysis. There has been in recent work, there have been some efforts made to eliminate the caustic materials or to not use caustic materials in the digestion, particularly of the of animals. And these approaches have been reported in the literature. One is a density separation methodology, and the other is an ultrasonic extraction methodology noted in the bibliographic reference below. So now we're going to actually get into some examples of analysis of microplastics collected from the environment and also collected from animals. And we want to acknowledge our collaborators at the Lamont Doherty Earth Observatory at Columbia University. They actually collected the samples and prepared the samples for us, and we did the infrared microspectroscopy analysis in our laboratory. So the filtered water samples that we're going to show you were collected from various areas of the lower Hudson River in New York through water collection and filtration. Oysters were collected also in the vicinity of New York Harbor, and then shrimp were sourced commercially from South America. So our first example is from a filtered water sample, and we see an image of this microplastic illuminated with oblique illumination on the right-hand side. You can see that the particle is roughly 150 micrometers in dimension, roughly circular or spherical. In this case, we were able to analyze this sample directly using attenuated total reflection, ATR. So we're actually viewing the specimen through our ATR crystal, as we showed you in the previous slide. Then we just touch the sample, utilizing, in this case, a 250 micrometer aperture with a 30-second data acquisition. And the spectrum of the unknown material is shown in the red at the top. This is attenuated total reflection spectrum of that unknown particle. And you can see that it is well matched to a commercial material, trade name Dispercol KA8299, which is a two-component polyurethane sample that contains poly 1,4-butylene adipate. And this material has extensive applications in injection molding, injection molded products in various industries. So in this case, we could not find any additional components for this material. And it might be a virgin pellet from a manufacturing process, or it could have been abraded from a larger material before being collected from the environment. Our next example is also a filtered water sample. And in this case, we're viewing a relatively small red fibrous material directly on the surface of the filter paper. So we're viewing this once again in oblique illumination, and you can see the size of the microplastic is roughly 30 micrometers by 300 micrometers. In this case, we removed the particle from the filter paper, placed it directly onto a low E-glass slide, and analyzed the material, flattened the material, and analyzed it in a reflection absorption mode. So we're reflecting off the surface of the low E-glass through the fiber material using a relatively small aperture in this case, 60 micrometers, and a 1-minute data collection. So the fiber that we observe, the spectrum of the fiber, is shown on the top, and we could very simply identify the bulk of the material as polypropylene. Reference spectrum of polypropylene is shown in the middle. But we're also able to identify another component, sodium octyl imino dipropionate, and this is an additive that has great resistance to acids and bases. And polypropylene has many applications in engineered plastics, but some typical ones are specialized water bottles as well as fibers to manufacture carpets. Because of the shape of this material, it could be that this is a carpet fiber. Another filtered water sample, we see that this microparticle is roughly 250 micrometers in dimension. Once again, we analyzed this directly with diamond attenuated total reflection using a 30-second acquisition time. The red spectrum is the spectrum of the particle, and the primary component is polyethylene, which has likely been oxidized in the environment. So in oxidized polyethylene, we see an absorption band here, which is not normally there in virgin polyethylene. That is a carboxylic acid carbonyl stretch due to incorporation of oxygen in the polyethylene chains. Polyethylene has a very broad range of application, but the fact that the habit of the material was in a bead form could lead back to a consumer product from consumer waste in wastewater treatment. The next couple examples are from samples collected from animals using that digestion and filtration procedure that we spoke about earlier. In this case, we're seeing a blue fiber collected from an oyster, and you can see the fiber, which is actually observed in this case not with oblique illumination but with reflection illumination, and this is directly on the surface of a low E-glass slide. I'm sorry, this is transmitted light illumination. I said reflection illumination in air. So with low E-glass slides, we're able to observe samples in transmitted or reflected light illumination, but they're very reflective to infrared radiation. So we record the spectrum by double pass reflection. through the material. And we can actually see in this case where we analyzed this fiber. So the fiber is only about 20 microns in diameter, but we flattened out a portion of the fiber to get an appropriate infrared path length, and that also increases the size. So in this case, we used 100 micrometer aperture, and the red spectrum on the top was the result. And this is easily matched to polyethylene terephthalate, or PET. Polyethylene terephthalate also has a lot of applications in engineered plastic products, including fibers. The Dacron trade name is polyester terephthalate, produced by the DuPont company, or should be still produced by the DuPont company. PET is also used in your soda, soft drink, and water bottles. So it's very, very common in the environment. This is a particle that was collected from shrimp, also using the digestion sample preparation method. In this case, we were able to analyze the material by diamond ATR using a 250 micrometer aperture and 30-second data acquisition. So the primary component of the sample, once again, was polyethylene, but you're seeing some absorption bands in additional to polyethylene. So this is a mixture. The polyethylene material is shown in the middle spectrum. We were also able to identify a secondary component, nitrocellulose, and there's another component, there's a third component that is present that we were not able to identify in this case. So the samples can be more than one material, and although we could only identify two components, we could see that at least three components were present in this one small 200 micrometer package, or 200 micrometer particle, excuse me. So with that, I'd like to conclude the presentation with some final thoughts. So microplastic pollution is becoming a very ubiquitous problem for us in our oceans and aquifers. Research has only really begun to brush the surface of the effects of microplastics in animals and humans. For those who consume shellfish, it is very probable that you are consuming some plastics. Microspectroscopy provides an affordable platform to help aid in identifying the microplastics in waste streams. Further identification of these microplastics waste streams will aid in the preservation of our oceans and our own health. And with that, I'd like to turn it back over to Lauren, who I think will ask you all for questions.
Awesome. Thank you so much, Dave. This was such a great presentation. I felt like I was watching some mini episodes of CSI here at the end. Lots of great information. All right, we have a couple questions. I want to dive right in. So the first question, how long did the analysis of microplastic samples in the presentation take?
Well, the infrared collection of the infrared spectrum, the collection of the infrared spectrum itself, measuring it, was a maximum of a minute. You have to collect the background spectrum, which is a blank, for those of you who aren't necessarily that familiar with FTIR. So it's a minute for the background and a minute for the sample. For these examples that we showed you, I think a couple of them were actually 30 seconds. So that proceeds relatively rapidly. Most of the time in an analysis is really taken up by the sample preparation aspects of it. And that can vary, with the sample. Unfortunately, there's no really single answer that's correct for how long that takes. surprisingly, the manipulation of microplastics and microsamples in particular, once they've been isolated, if you have the right tools, it is really not that difficult to manipulate samples on the micrometer size scale and prepare them for analysis. So it can take several minutes to get a sample in a presentation that's appropriate for infrared microanalysis. You know, if you want to use a rule of thumb, maybe 5 minutes is safe. Placing a sample under a stereo microscope, maybe manipulating it and isolating it, and then in some occasions, you have to roll it out. You have to thin it to get an appropriate infrared path length before you analyze it. But with the ATR device, we've attempted to eliminate some of the steps by, in the case of ATR, the sample path length is determined by the ATR element and the optical properties of the sample. So you don't have to thin it. So it removes one of those sample preparation steps. And with some of the microplastics, we're actually able to analyze them directly on the filter selectively. So they don't even have to be removed from the filter or substrate. So I would say to get back to your question, maybe 5 minutes of sample preparation and a couple minutes of data collection at the max.
Great. We have another question. In your experience, what is the smallest size microplastic that can be analyzed under the different FTIR modes?
So in our device, the smallest aperture that we use is 60 micrometers. You can analyze samples that are smaller than that, 50 microns, 50 micrometers or less. For the unaided human eye, a good rule of thumb is that the human eye can see materials 100 micrometers and greater. So a 60 micrometer aperture size is less than what humans can observe with the unaided eye. And then another factor is the detector itself. So in the low-cost compact FTIR spectrometers, typically that is a deuterated triglycine sulfate detector. In some other spectrometers, one can mount what's called a mercury cadmium telluride detector, which is much more sensitive detector than TGS, but it requires liquid nitrogen cooling. With that kind of detector, you can analyze specimens which are 10 micrometers or greater because of the sensitivity of the detector itself. But most commonly with SurveyIR, a deuterated triglycine sulfate detector is used.
Great. Another question is, how do you determine which measurement mode is best for your sample analysis, like ATR, reflection, or transmission?
So once again, that will depend on your sample. We would want to try to use ATR as frequently as possible due to its ease of use, and you're going to get a high quality spectrum with a very reproducible or uniform thickness, because the thickness, as I said, is determined only by the optical properties of your sample and the diamond element. So we try to analyze samples in that mode if we can. And so with these samples, the microplastic samples, if you view the sample in oblique illumination, if you could see a little bit of shadowing, because the oblique illumination comes in at an angle, you'll see a shadow. That tells you that your sample is extending above the surface of the filter. And in that case, you'll get in most cases, very good contact between the sample and the diamond ATR element, and you'll selectively measure the plastic from its substrate. So if the plastic is embedded in the filter material, or it's really very thin, then you get better results by removing it from the filter paper and putting it onto what we call Lowy glass slides, which are really microscope slides. They are glass substrates, but they have an infrared reflective coating on them. We thin that out with a roller knife, and you probably don't know what a roller knife is without looking at it, but it's a knife with a bearing on it, and that thins the sample out. And then we analyze it by reflection absorption in that way. If we analyze it that way and the sample is still too thick, then we could get better results by measuring it in transmission through an infrared transmitting window, because the path length, in reflection, the path length is double because you go in through the sample and then come out through the sample, so you pass through it twice. If you measure it in transmission, you only pass through it once. So we very rarely use transmission with these samples, but with paint chips, for instance, which can be sometimes difficult to get to an appropriate path length, then transmission is more than often used in that case. Transmission or ATR, depending on the habit of the sample. So when I say the habit of the sample, it's the environment in which you see the sample when you're observing it under a microscope prior to getting it to the FTIR. And some of this is a little bit of experience. When you start looking at samples, you gain a good knowledge of what is going to be the most appropriate method.
Awesome. It looks like we are at the end of our time here. I want to say a big thank you to our partners, Zytec and Dr. Shearing. Thank you so much for today's webinar. To everyone who attended, before the end of the week, you'll receive an email with a link to this recorded webinar. And we want to thank everyone for joining us, and we hope you found this topic informative. I know I did. After the webinar, we ask that you take a 30-second survey. There's only 3 questions, and this information helps us understand how effective our webinar format is, and also gives you a chance to help dictate future webinar topics. All right, that is it for us. Have a great day, everybody.